So temperature controls, simple ones that are going to do needing to make sense. Solid state controls, these are your more high tech kind of thing. Whenever you see something that says solid state, it means typically it's going to mean control board. That's I hate seeing the screen in my eyes. Just weird. So the solid state functions, these are going to be our control boards, our different various devices and everything like that we're going to see used as a means of control for our HVAC system. Basically it's going to be, and right here where it says, use primarily control, protect, or start one function in equipment operation. So prevent the system from short cycling, allow for motor protection, simple temperature controls, pretty much all the things right there where it's listing. That's what we're talking about for solid state controls and solid state devices. These are going to feed back to that board information saying, yes, we're good, we can go ahead and start, or no, it's going to block the path for electrical flow. One of the most common ones you're going to come across, residentially especially, is an electronic timer. This is very, very common here in Virginia because we're dealing with heat pumps a lot of times. Because we deal with heat pumps a lot, one of the big things with it is you've got a reversing valve. Now, you all learn about exactly how a heat pump operates and everything like that, but basically, it's a refrigeration. It's going to take the refrigeration cycle, the air conditioning cycle, that compressor, condenser, expansion device, evaporator, back to the compressor. It's going to take that cycle, and it's going to reverse it. Now, to reverse it, that takes a lot. One of the things that you have to make sure is you want to make sure that the pressure is not uneven on either side of the compressor when it starts up. You want to have it where everything's back at what's called equilibrium, where everything's the same. So if you have your gauges hooked up to a system while it's running and operating, your high side gauge will be a much higher pressure than your low side gauge, obviously. That's what's going to happen. You can hook your gauges up to a system when it's off, and the needles will both be at the same exact pressure, where they should be. They should both be, let's say, 200 PSI. But once that system starts to run, you should see your high side go up and your low side pressure go down. What can happen a lot of times is when a system is switching between heating and cooling, for a heat pump especially, if it's been some crazy weather like we have in Virginia, where one day we're heating, the next day we're cooling, the next day we're heating, we need to allow the system to give itself enough time to restart. And the other thing is, even if it's operating normally, heating or cooling wise, that pressure change is going to happen. We're going to have lower on one side, higher on the other, all right? And we need to get it back to equilibrium before we start the compressor up again. To ensure that it has time to get back to equilibrium, this is why you have electronic timers installed a lot of times. Now, sometimes it will actually be a big switch like this. I've seen it a lot of times. That's how it's actually operated. You can see right here on the top, it's got a dial with an arrow, and you can actually put your screwdriver right in there and then turn the dial or the arrow to whatever amount of time that you want. So this isn't the most accurate thing. It's got clearly labeled 5 minutes, 10 minutes, and 0.03 minutes. Don't know how little bit of time that is. It is very, very short. So it's a lot less than a minute. What would it be exactly if it was soon to do math? 60 seconds, what, like 8 seconds? I think something like that. From off the top of my head. Oh, crap, now I'm going to check my math. 1.8 seconds, not even. So if that's truly 0.03 and not 0.3. If it was 0.3, it'd be 18 seconds. Still a small short delay, but typically 5 minutes is your most common delay. Now, where this comes into an issue with us as far as troubleshooting is when it comes to turning a system on and off. Right? When you turn a system on and off, one of the things that's going to happen is this delay will activate. It's going to turn on. And it's going to make it so that you disconnect power, connect back in. Should turn on right away. No. this right here will deny power to the system for whatever that timer is set for. So for this one, it's got it where it's currently set at 10 minutes. It would wait 10 minutes before it would even turn the system back on. Now, here is the biggest thing to help you from shooting yourself in your foot when you're looking at these kinds of timers and delays, all right? Set a timer yourself. Whenever you reset a system, start a clock on your phone, start a stopwatch. If you gotta watch, do the stopwatch little thing on it or on your phone or whatever. Don't count on the 1 Mississippi's. Don't count on the, oh, I think I know how long 5 minutes is. No one in their right mind knows how long 5 minutes is until they've truly had to wait 5 minutes for an air conditioner to come back on. It's nerve-wracking. Because, like, if you don't have that timer going, you really don't know. It might have been 5 minutes, might not have been, So it's a really tough thing for people to get that they run into from time to time. It's just, oh, I'll just guess what's 5 minutes. How hard could it be? Incredibly hard. It's one of those things that I just always recommend. Just start a timer. You don't know how long 5 minutes is until you start really working with 5 minute delays. And even then, you don't know how long 5 minutes is. Because it'll be cold outside, it'll be hot outside, and your brain will think, oh, 5 minutes has already gone by. It might have been only 90 seconds. So just be patient, wait the 5 minutes. These are really good for, just making sure that we have it where a system delays itself. This is also a really good way to stop short cycling. Not just making sure that, yes, the pressure's equalized on a air conditioning or heat pump cycle, but also making sure that we have my God, my brain just farted. We don't have a system short cycling. There we go. Took a minute. So short cycling is when a system is constantly cycling on and off and on and off and on and off, back and forth, back and forth. That's what we're talking about with short cycling. So for this system, typically the short cycling is an issue with the system when it's trying to just basically fire on again and again and again, even if there's not a call for cooling or something like that. Putting in a time delay or something like that can prevent that system from doing that. And preventing it from doing that can help prevent it from damaging itself. Short cycling is one of the most damaging things that a unit can do to itself, is to try to come on in a very short, worst thing it can do with short cycling, where it's trying to come on multiple times in a very short amount of time. That can damage contactors, capacitors, compressors, condenser fan motors. Pretty much every component on an HVAC system is damaged by short cycling. But one little tiny part, this electronic timer, this time delay start, it basically makes it so that there's one less way that the system can hurt itself, or it's not going to do it as often. And a customer will notice at that point, if they have a system that's short cycling, another thing they're going to see typically, not all the time, is the system will also cut itself off on high amperage sometimes. And this is something that can help it, where the customer doesn't call in because the system's short cycling. They call in because it's not running enough. It'll run for a minute, cut off, stay off for 5 minutes, 10 minutes, whatever the delay's set to, and then come back on, but only for a couple of minutes. And that's because of, it could be high amperage, could be high pressure, could be a lack of airflow, could be any number of problems, but this makes it so that we don't have the motors constantly trying to kick on, because the motors are going to try and solve the problem. Oh, it's cool, it's not hot, or it's too hot in the house. Well, let's turn all the motors on. Let's turn on the compressor and the condenser fan motor and the blower motor and get that cooling process to start. The problem is, if the motors aren't working or the pressure systems are shutting it off, they're only going to wait until that pressure or the temperature, whatever kind of delay, if it's a pressure or temperature delay or switch, all it's going to wait for is once the pressure gets back down to normal, once the temperature gets back down to normal, then it's going to fire right back up again. So having it where it's not a pressure or temperature, but literally just time is all it's waiting for, that's one of the biggest advantages to these systems. So these are two different types of electronic timers that you can see. There's delay on make timers and delay on break timers, all right? Your book goes into pretty good detail explaining the difference between the two, but the basics are listed right here on the slide. Delay on make timers, delay closing the device for a predetermined period of time. So that's always going to be 5 minutes, 3 minutes, 4 minutes, whatever it is. No, we're not letting the system turn on like I was talking about before. The other ones are delay on break timers, delay an electrical component from being de-energized when operating control opens. So this would be something more for your blower fan motor. This is a very common thing to have for the fan motor on a gas furnace or for an electric furnace. One of the things is, if a furnace is burning and operating, it's creating a lot of heat, right? When it shuts the gas off, that doesn't mean it stops producing heat. The metal that it's heated, the heat exchanger, if it's a gas furnace, or the electric coils for a electric resistance heating, it looks similar to honestly, it's if you wrap a really thin wire around in a big old spring and you just threw electricity through a giant spring, that's what it looks like almost. Those hold a lot of heat onto them for a period of time, even after our heating process is done. So delay on break, delay an electrical component from being de-energized when operating control opens. The operating control that opens is the thermostat says, hey, we've got enough heat in the house, we're good. Go ahead and shut the electric or the gas furnace off. But the delay on break says, keep the blower motor on in the house, all right? Yes, we've got enough heat out in the house, but we haven't cooled off our heat exchanger or our electric heat strip enough. And we need to move a little bit more air across that until the temperature drops down on that. And that will be for a specific amount of time. For the newer ones, that's what it's going to be. Old school, it used to wait for the systems to get to a certain temperature. It would actually have a temperature sensor near your electric heat kit, near your heat exchanger to tell the blower fan, yes, the electric heat kit or the blower fan have cooled off enough, you can turn off the heat or turn off the fan motor. Nowadays, it's literally just a timer. And these are going to be, you can actually get individual controlled delay on break electric timers, or they're going to be integrated into a furnace control board or a fan control board or something like that. That will make it so that the basically everything goes back to that board still. And on that board, a lot of times you'll have it where there will be a set of dip switches or dual inline pair switches. And those will actually have it where they can be turned on in different directions and everything like that to control whether or not it's whether it's going in heating mode or cooling mode and how long of a delay. That's the other thing. So for heating, you can have it where that fan stays on for a longer period of time versus the cooling mode. You want the fan to cut off, maybe 30 seconds after it's done going through the cooling cycle. Electronic timers, again, you're going to see them. There's all different styles and sizes and types, but they're going to be used for a lot of different things. This right here, what it's showing is an anti-short cycling device. This is literally a device made to stop short cycling. I talked about it a minute ago, saying that those delay timers can be used to help to stop short cycling, but this is what's used more often than not. So basically, it's going to be 30 seconds to 5 minutes. It'll be some sort of electronic delay, and it's just going to make it. Basically, it's waiting for. It's going to wait for electric charge to calm down, pretty much. As far as let the motors lose some of their charge, let them lose that magnetism, because even after we shut power off to all of our coils and windings and everything like that, there's still a little bit of residual electricity there, not enough to do anything with, but enough to still create a magnetic field and to have a little bit of heat still present there. So to prevent that from happening, these typically look at the amount of amperage, they look at the amount of magnetism that's left in the system, and until it drops down, it's not going to allow power to come back into it. Because the last thing you want is a motor that was just turned on, turn it on again. That's like, take a car from off and then on, start it, on, turn it off, start it again, turn it off, start it again. That's ridiculous. That's a waste of energy. That's a whole lot of battery power you're using, a whole lot of fuel you're using, and you're wearing down the motor because startup is one of the biggest things that's going to wear down an engine or wear down a motor. For us, that's what we're concerned about a lot of times, is that excessive amount of power and electricity can actually lead to a lot of problems with our systems. So electronic devices for electric motors, again, solid state devices, like I said, control boards are used a lot of times nowadays for these systems. Typically for single phase motors, you're going to see a lot of solid state devices used. Three-phase motors use different controls. They're a little bit odd. They're not going to be watching the same kind of thing. So for a single phase motor, we're only dealing with one phase of electricity, so we only have to worry about one leg of power. So we really only have to control current flowing in very, very small batches. You got your start and run winding, your common, that's it. It's not really like we have to control all three legs of power or anything like that. So that's what makes it really nice. Again, look at your book. It's got it. Section 9.4 really goes into detail about this whole thing. But we're going to see solid state devices used typically a lot in the industry, especially for single phase systems. Overload protection, we talked about overloads already. Overloads, they're going to be the main thing that we see for a as your most basic style of safety or control for a motor. Most common overload, always going to be a fuse. All right, so we can use it for three-phase, we can use it for single-phase. You're going to see it where overloads are used on just about everything, because I want to try and make sure we're not, the last thing we want to do is go into an overload on an HVAC system. Again, we've got where there's devices specifically for single-phase and for three-phase, like I was saying earlier. One of the things it's talking about here is single-phase conditioning, right? Three-phase systems, makes sense that they would have three phases of electricity. The problem is when they decide not to have three phases of electricity. When they decide, you know what, let's all sync up and be one single phase. Oh, that causes a lot of problems. The main thing amongst that is the fact that pretty much none of your motors or components are actually going to be working if everything's on the same phase. So having it where you've got something that's going to watch and make sure that it doesn't go into a single phase system from a three-phase system going into a single phase system, this helps protect a lot of the different components, all of our motors and everything like that. So really just trying to stop the load, protect it, disconnect our power, make it so that we have the fastest way to control and protect our motor. Yeah, sure, we might not have heating or cooling. We might lose the process of, let's say, refrigeration for a certain amount of time or something like that, or a freezer might stop working. But we didn't have go? A motor. And I'd much rather have it where an HVAC tech has to go out there, and a customer's much happier to have an HVAC tech go out there and replace a $10 fuse or a $5 fuse or a $1 fuse compared to having to replace, a $5,000 motor. It's just the truth of the matter. People want to, yeah, I'll replace the fuse all day. I got no problem with that. I'll pay the dispatch. I'll pay the $89 dispatch fee. I'll pay your $55 diagnostic fee. I'll pay your parts fee of an extra $10. I don't care. 160 or 140 or 150 bucks is a whole lot cheaper than 5,000. I'll pay up to $500 if it makes it so that I'm not having to deal with this $5,000 bill. And that's why these safeties and controls are installed in these systems, because manufacturers see ahead of time. They understand what the needs and wants of their customers are, and the needs and wants of technicians. Technicians don't want to have to deal with replacing compressors every single freaking day. Sure, it's a lot of work, but oh my gosh, it's a lot of work. Like, yeah, you make money, but oh my gosh, you're breaking your back every single day doing crazy compressor installs again and again and again and again. It's annoying after a while. You want to have some variety and spice of life. So to protect these kinds of units and these kinds of components, they have it where they've got these extra devices to help it out. This is the other thing that can happen as well, all right? So three-phase electricity, you've got it where it's typically going to be coming and it's going to have three phases. So we'll have, oh geez, this is going to be real bad. I'm just letting you guys know. I have a second phase. Oh, let's see if I can get a third phase in here. Third, something like that. All right, so let's just call them A, B, and C. Okay, that's a work of art. So our A, B, and C phases, they're just a little bit out of step with each other on this horrible graph. Please judge me. Don't judge me. Please don't judge me. So we got it where they're out of phase and everything like that. But what happens with a phase reversal is, okay, if you've got a motor and it's hooked up to A, B, and C on terminals, let's say 1, 2, and 3. Now, this is just an example. There's a lot of different ways you can wire up these motors, and depending on the manufacturer, it's going to change certain things, but very basic stuff. 3-phase motor, 3 terminals, all right? I'm going to connect A, B, and C to those terminals. Now, if I have a phase reversal happen, here's what can occur. My A can become my C, B might stay B, and that's going to go to A. Now, switching those two around, I've now made it where, let's say this was going clockwise. Now it's going to go counterclockwise. I have reversed. By reversing the phases, you can reverse the rotation of the motor. Whether that's a blower motor for a fan, a condenser fan motor for a outdoor unit. So instead of pulling air through the coil and up out the top, it's going to push air down into the coil and out. Or a compressor is going to throw refrigerant in the opposite direction. It'll throw it backwards. Phase reversal is a major, major issue if it occurs. Basically, it's going to make it so that the motor, by going in an opposite direction, is going to, cause the system to not operate properly. Now, your unit might not get damaged. You might have it where you can deal with it. It might be okay for a little while, but you're going to have a lack of heating and cooling. If your airflow and your refrigerant flow is in the wrong directions, then you're not going to have anything working how it should. So again, that's the whole thing with these is that you're going to see a lot of these causing not major problems until they've been running for a little while. And having a phase reversal protection device makes it so you don't have to worry about it at all. It'll stop the system from operating if it sees a phase reversal. So, multifunction electronic motor protectors. Again, these are ones that we're going to see for a lot of different things. Phase loss, phase reversal, short cycling, overloads, current imbalancing. If you got it where amperage is really high on one side of the motor, on one winding compared to another or something like that, because of increased resistance or decreased resistance, that's when you're going to have these different issues going on with the motor. Having these devices allows it so you can actually check and maintain those different components. So heat pump electronic modules, again, these typically you're going to see a couple of different things with them. Most of the time it's going to be defrost control boards for residential systems. Depending on, it'll also control the contactor, it control sometimes a time delay as well will be built into this. So a heat pump control can actually do a lot. It's not just one device to make sure, oh, the heat pump's operating as it should. No, it's going to check the contactor. It's going to check and make sure that our temperature is increasing, that our pressures aren't, off or anything like that, that our time delay's been, monitored. So it can get a lot of information. It'll also, one of the big things with the heat pump electronic module is that it's going to have typically, for more sophisticated systems at least, or for more modern systems, you're going to see it where it will include an outdoor temperature sensor, ODTS. Or an OTS, outdoor temperature sensor module. These are going to be, or an outdoor temperature sensor is going to feed information back to that module to tell it, okay, hey, this is how cold it is outside. Now, the reason why this is important, especially for heat pumps, it's important for pretty much all systems to know what the temperature is outside when they're in heating mode. but for a heat pump especially, because when a typical heat pump gets close to about 40 degrees and gets closer and closer to that freezing temperature of water, 32 degrees Fahrenheit, that's when we're going to see an outdoor unit start to build ice onto it. If you've ever gone out to your unit out in the wintertime and you've looked outside and you see ice on the outside of it, that is it frosting up. That's it freezing up. Now, this happens for a couple of different reasons. Now, if the system's failing, it can frost up because of a lack of refrigerant or a lack of airflow. So change your filters and make sure that your coils are clean, and make sure that your refrigerant is properly charged. For the other reason that it will occur is just because if it's in heat pump mode, that outdoor unit is getting colder and colder and colder. When it gets colder, water condenses onto it, and that water will freeze as it gets to freezing temperatures outside. So to prevent this from freezing up and then have to go into this defrost cycle and do all these different things, an outdoor temperature sensor can let the system know ahead of time, hey, we're probably going to freeze over into a block of ice in the next, 20, 30, 40 minutes, or in the next cycle, or it will tell it before it even kicks on, hey, it's too cold outside, just turn on the electric emergency heat, because if I come on, I'm just going to turn to a block of ice in the next 30 seconds. When it gets to below 32, that's pretty much what occurs. That thing turns into a block of ice. For a typical system without the outdoor sensor, that turns into a block of ice. Okay, go into defrost mode, kick on the electric heat. It'll kick on the electric heat, go into defrost mode until that outdoor unit is melted. And then as soon as it's melted, guess what it does? It's right back into heat mode again. Turns back into a block of ice, kicks on the electric heat again, and it just keeps cycling and wasting power. With these module controls for the heat pumps, this allows you for the heat pump to actually tell itself, hey, stop wasting energy and just keeping to try to do this 5 minutes of heating from the heat pump. We're just going to run on electric from this point out. So that's one of the nice things about that. So again, going to receive input from a lot of different controls and devices. So we've got gas furnaces. Y'all learn more and more about these modules when you get into the gas furnace class HVR155. These will be things that will control all sorts of factors. The big thing that it's going to control is what we'll learn about is called the order of operations, which includes all of these things, making sure that a pilot's lit safely, pre-purge and post-purge, blower motor operation, electronic control board, safeties, diagnostic codes, like I was saying before with the LEDs, that's usually on these IFC boards, or the electronic control modules, ECM boards will have it where they're going to be, IFC stands for integrated furnace control. And it's going to be that part and that control that's actually going to be the factor to, help you diagnose a lot of stuff with that furnace. So, again, oil furnace, electronic controls, you're going to learn a lot about these when you go through your oil furnace heating class. The big thing to understand, I guess, when anything that's different from an oil furnace that you're not going to see on anything else is something called a CAD cell. CAD is short for cadmium sulfate. It's a material that's conductive, and it's reactive to light. So it's a really cool device that we use as a safety for an oil furnace to make sure that the oil furnace has ignited. Basically, this CAD cell looks for a light because if it's got ignition and it's got a flame, there's going to be light producing off of it. So it senses that light. When it sees the light, it knows, yep, we've got a flame and we're burning fine, and let's keep the oil flowing and keep the flame going. And that's pretty much all it does. You can actually measure and test a CAD cell with the light from any kind of light. The easiest way to do it is it's going to have 2 leads to it, all right? And you can actually see if you cover it up, you cover up that CAD cell, and you put your leads from your meter into the 2 wires going in and out of that CAD cell. You cover it up, you will see resistance build up. You'll see it go higher and higher and higher. But then you take your thumb off and you uncover that CAD cell and you put it towards a light, or you put like a flashlight right over it, and you'll see that resistance drop quickly because it's reacting to light. And that's a way to test CAD cell. They're cheap parts, they're easy. They don't take a lot. Always keep them on your truck. But you all learn about oil furnaces, like I said, HVR160. That's when you're going to be going more into that. And you'll learn much more about the electronic controls. This is the main thing I want you to understand right here at the top of this slide: black box approach. Check your inputs, check your outputs. That is the easiest way and the most successful way to check a modern control board nowadays most of the time. You know, there's going to be other ones that will tell you how to test it, that will give you step-by-step instructions. You might be able to get in contact with the manufacturer that lets you know how to do things their way. But the black box approach is probably your simplest, your easiest, and your most consistent one, because you're checking to make sure, okay, is voltage coming in? Is voltage going out? That's it. If it's coming in and it's not going out, and it's supposed to be going out because there's a call for heating or there's a call for cooling, then you've got a problem with the board. At the end of the day, you've got a problem with the board. So you'll have it where you've got a lot of different things that you can find with that. Again, like it says right here, microprocessors, going to give you a number code with these really nice ones. They'll let you know exactly what number. Say, you know, number 45 is what our status is. The status could be inducer draft motor failed to pull a vacuum or something like that, or pressure fail switch, pressure switch failed. There we go, not pressure failed switch. Pressure switch failed. You know, whatever it might be, it'll let you know with that code. And that might not be replace the pressure switch. It might be go look at the pressure switch, you know, and see what exactly is going on with it. So that's pretty much the end of chapter 12 for us. Again, we've got a lot of different controls and electronic control devices that can be used in the HVAC system for, you know, solid state and time delays and all these different things. Just keep in mind, you know, what all we've got going on with these. Make sure to continue to read up chapter 12. We're going to go over chapter 13 on Friday. And that'll be our for the end of the week and everything like that. So this will be it for today.